The visitor that made no sense in late 2017, something entered our solar system that had never been seen before. It came without warning, without ceremony, and left just as suddenly. Astronomers in Hawaii named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was the first confirmed object from another star system to ever pass through our solar neighborhood. But as it moved, spun, and accelerated, nothing about it made sense. Oumuamua didn't behave like any known asteroid or comet. It tumbled through space erratically, not spinning along a simple axis like most space rocks do, but flipping in an elongated, almost comical way, as if it were a shard of something broken. It was shaped not like a sphere or even a lumpy potato, but more like a flattened cigar, or perhaps even a pancake, hundreds of meters long, but just tens of meters wide. It reflected sunlight in strange, uneven pulses. And then, as it left, it began to accelerate. Slightly, but measurably. This acceleration, a gentle push outward, away from the sun, was unexpected. There was no visible trail of gas or ice, no tail like a comet might have. It was as if the object had a silent propulsion system, or was reacting to sunlight in a way no one could fully explain. Some scientists proposed that it was shedding invisible hydrogen gas. Others speculated its flat shape made it respond to solar radiation pressure more like a sail. A few, including Harvard astronomer Avi Loeb, wondered aloud if we had just witnessed an alien probe. A piece of alien technology, not functioning, not signaling, but coasting. Most scientists rejected the alien idea, not because they had better answers, but because extraordinary claims demand extraordinary evidence. And Oumuamua had already passed us by. Too fast for a second look. Too distant for further data. It slipped away into the dark, leaving only 11 days of close observation. 11 days to define and debate an enigma that may never return. But the mystery wasn't just its motion or its shape. It was the sheer improbability of us seeing it at all. Interstellar objects must drift for millions, even billions, of years in the cold between stars. The odds that one would pass close enough for our telescopes to notice, during the brief sliver of time we've even had the tools to look, are staggeringly small. Which raises another question: was this the first, or just the first we noticed? Some speculated Oumuamua might be a fragment of a shattered planet, flung outward from its system long ago. Others imagined it as a relic, an artifact of something vast and ancient, now inert, reduced to debris. If it were artificial, it might have long outlived its makers. If it were natural, it might still tell stories no one on Earth can yet read. It carried no signal, no light, no call. But it was seen, and that may have been enough. Oumuamua reminded us that the universe is far more chaotic, and far more filled with silent travelers, than we imagined. It hinted at histories in motion across light years, at messengers that arrive without words, and leave without answers. Its very name, Scout, or Messenger, now feels prophetic. The second known interstellar object, Borisov, came soon after. But it behaved more like a classic comet. Cold. Composed. Familiar. Oumuamua was none of these things. It was a flicker in our sky, a question mark on a cosmic scale. And perhaps that's its message, that the universe is still full of questions, and that not everything we observe will fit the shapes we know. That some truths will pass through us like ghosts, impossible, unprovable, unforgettable. Because sometimes, the most alien thing isn't what we see. It's that we saw it at all. Imagine a planet not of rock or ice, not of gas or flame, but of diamond. A world forged in the deepest furnace of the cosmos, its surface shimmering not with oceans or greenery, but with the lattice glint of crystallized carbon. This is not fiction. This is 55 Cancri, an exoplanet 40 light-years away in the constellation of Cancer, orbiting a sun-like star at blistering speed. 55 Cancri resembles a searing ember, temperatures reaching nearly 2,000 degrees Celsius, enough to vaporize any notion of habitability. It races around its star in just 18 hours, so close that its surface is likely tidal locked, one side always facing the fire, the other frozen in a stony shadow. But beneath its molten crust, scientists believe lies a secret. Due to its density, composition, and host star's chemistry, rich in carbon and poor in oxygen, the planet may be forged mostly of graphite and diamond. Trillions of carats. A planet-sized jewel gliding through space. We imagine diamonds as symbols of beauty, value, permanence. But here, in the cosmos, they are born of violence. Of pressure so intense it rewrites the nature of matter. 55 Cancri is not a treasure trove waiting for miners, it is a crucible. The diamond here is not cut, not clear, not ring-ready. It is likely jagged, buried, impure, the product of unfathomable geologic warfare inside an alien mantle. Yet still, it gleams in theory, and the idea shines through science. In our dreams, diamond planets suggest value beyond understanding. But in reality, they remind us that rarity on Earth is abundance elsewhere. Gold rains on neutron stars. Ice forms at the edge of light years. And carbon, the basis of our bodies, hardens into crystal in deep alien worlds. One day, we may see this world not only through light curves and spectral data, but through the eyes of probes or telescopes unimaginable today. Until then, 55 Cancri remains a cosmic metaphor that even in the vast brutality of space, beauty can form, not in spite of pressure, but because of it. Not all planets belong to stars. Some are cast out, flung from their birth systems by cosmic violence, left to wander alone. These are the rogue planets, massive, cold, and ancient travelers drifting through the interstellar void, orbiting nothing but the galaxy's center. No sunrise. No seasons. Only darkness. Estimates suggest there may be billions of such planets in the Milky Way alone, possibly more rogue planets than stars. Some are gas giants, others rocky Earth-like bodies. Some formed near stars and were ejected by gravitational slingshots. Others formed alone, collapsing from dust clouds like failed stars. They move in silence, invisible in ordinary light, revealed only by the rare dance of gravity or the faint whisper of thermal glow. On these planets, night is not a cycle, it is existence. No sunlight warms their surface. Yet paradoxically, they may not be frozen dead worlds. Internal heat, radioactive decay, or even residual formation energy can keep them warm beneath the surface. In theory, oceans could exist under layers of ice. Entire ecosystems might bloom beneath crusts, heated not by a sun, but by planetary fire. Imagine such a world, black skies above, but beneath the surface, life. Microbial, maybe, or more. Entire biospheres sealed in eternal twilight. These planets would be immune to solar flares, supernovae, or stellar death. In fact, they might outlive their sunbound cousins by billions of years, surviving long after stars flicker out. Some theories go further. Advanced civilizations could have sought these planets deliberately, using their anonymity, coldness, and mobility as advantages. A rogue planet is a perfect hiding place. No infrared signature. No orbit to trace. If you're looking to stay hidden in a galaxy full of watchers, why not cut the lights and drift? To us, rogue planets are whispers in the dark. But to others, hypothetical or real, they might be havens, laboratories, or even homes. Their silence is not absence, but insulation. Not emptiness, but protection. In the end, they remind us, stars are not required for wonder. Life, warmth, and mystery can persist in the loneliest corners of space. The cosmos has no single path. And some worlds, like some ideas, thrive best when unbound. In the vast theater of the universe, some worlds form not from dust and flame, but from pressure, carbon, and the slow alchemy of stellar death. Among these exotic objects is 55 Cancri, a planet that captured headlines for a single staggering claim. Made, in large part, of diamond. Located around 40 light-years away in the constellation of Cancer, 55 Cancri orbits a sun-like star in a tight, blistering orbit, so close that a year there lasts just 18 Earth hours. It is a super-Earth, larger than our home planet but smaller than gas giants, with a mass roughly 8 times that of Earth and twice the radius. This makes it one of the first discovered rocky exoplanets that showed signs of being truly alien. What makes 55 Cancri so astonishing is its chemical composition, inferred from its star. The host star is carbon-rich and oxygen-poor, a condition that leads to very different geologies than Earth's. Instead of silicates and iron dominating its structure, a carbon-rich environment means the planet may have formed with abundant graphite and, deeper down, diamond. In such a scenario, under immense heat and pressure, thousands of degrees Celsius near the core, carbon atoms squeeze into tight lattices, forming massive layers of diamond. Unlike Earth's diamonds, buried in veins and accessed through volcanic pipes, these would form as a mantle-wide material. We are speaking not of treasure chamber crystals, but of planetary geology made of gemstone. But 55 Cancri is no glittering gem in space. It is an extreme world, tidally locked, with one side scorched by eternal daylight and the other frozen in night. The dayside temperatures soar above 2,400 degrees Celsius, 4,352 degrees Fahrenheit. Hot enough to vaporize most metals. There's likely no atmosphere, or if there is, it's transient, burned away and replenished in cycles. Early studies suggested a possible lava ocean covering part of the surface, vaporized rocks circulating in a horrifying, molten weather system. Yet beneath all this chaos may lie diamond beds, stretching for thousands of kilometers, layered beneath graphite crusts or infused within carbon-rich rock. If we could slice the planet open, its interior might resemble a geologist's fever dream, dark, dense, and glinting in strange geometric fractures. Naturally, the media dubbed it the Diamond Planet, but scientists were more cautious. Subsequent observations complicated the picture, detecting possible signs of water vapor or silicates instead. The truth is still hidden behind telescope resolution, yet the idea remains plausible in certain formation scenarios. Regardless of the details, 55 Cancri reminds us of this: value is relative. On Earth, diamonds are rare, forged deep in our mantle under high pressure, prized for their hardness and clarity. In the cosmos, carbon is abundant, and under the right conditions, diamond can be as common as granite. One could imagine civilizations far advanced from us regarding diamond not as precious, but as mundane infrastructure. Bridges made of it, satellites plated in it, statues carved from gemstone. On a cosmic scale, our values melt away under new physics. And perhaps more striking than the diamond hypothesis is what this planet says about us. That we saw a data point, a weird orbital period, an infrared blip, and from it, envisioned a world of crystal. That imagination filled the gaps of observation with possibility. Science does not destroy wonder. It expands it. 55 Cancri may or may not be a diamond world, but it is absolutely a world of wonder. It exists, and that is enough. In the ink-black reaches between stars, where light fades and silence rules, wander the loneliest travelers of the galaxy. They are the rogue planets, worlds flung from their stars, untethered, unbound, moving through space with no orbit, no sun, no sunrise. These planets do not belong to any system. Some were born like stars, collapsing directly from gas clouds. Others were once loyal satellites, ejected by gravitational chaos, a close pass from a sibling giant, or the flick of a dying star's tantrum. However formed, they now move alone. And they are numerous. Recent estimates suggest that for every star in the Milky Way, there could be 2 or more rogue planets. That means hundreds of billions of worlds, hidden in the dark, unlit, undiscovered, invisible to our telescopes unless they pass in front of distant starlight or emit faint infrared warmth. Imagine them as frozen tombs. Without starlight, wouldn't they be dead? But nature is rarely so simple. Many rogue planets may retain internal heat, from formation energy, radioactive decay, or pressure, enough to keep subsurface oceans liquid beneath miles of insulating ice. Some may even support hydrothermal vents, much like Earth's ocean floors. Where there is water, warmth, and time, there is the potential for life. Such ecosystems would be sealed from the sky, life in caves, in oceans, beneath pressure and darkness. No stars would guide them. No seasons would shape them. Evolution would write new scripts entirely, organisms that sense thermal gradients rather than photons, that navigate by magnetism or vibration. These are not mere hypotheses. Europa and Enceladus, moons in our own solar system, may already host such subsurface oceans. If they can do so near a star, then rogue planets could do it in the dark. With far more time. With far fewer interruptions. But rogue planets are not just biological curiosities. They may be refuges. If a civilization wanted to hide, escape, or survive galactic catastrophes, rogue planets offer natural stealth. No light signature. No orbit to track. Covered in ice, perhaps cloaked with technology, they could drift for millennia between stars, undetected. In science fiction, they're often portrayed as wastelands or prisons. But what if they are arks? Worlds where life begins again, or where secrets sleep. Where vast libraries are etched into diamond-hard crusts, waiting for retrieval. We may never detect them en masse. They don't pass in front of stars. They emit little heat. Finding one is like spotting a whale in the ocean by its exhale alone. And yet they're out there. Drifting. Waiting. Not barren. Not forgotten. The galaxy is not made solely of light, but of shadow and silence too. And in that silence, whole histories may move, unseen. Among the strangest and most extreme relics of the cosmos are neutron stars, stellar corpses crushed into spheres the size of cities, yet denser than anything else in the observable universe. Imagine a mass greater than the sun, compressed into a ball no larger than Manhattan. Now imagine, upon this dense and featureless surface, tiny structures only millimeters tall. Mountains. But on a neutron star, even a bump the height of a paperclip is astonishing. When a massive star ends its life in a supernova, its core may collapse into a neutron star. The implosion fuses protons and electrons into neutrons, packing them so tightly that the resulting object resists further collapse only through neutron degeneracy pressure, a quantum mechanical effect. These stars are composed almost entirely of neutrons, arranged in exotic structures that scientists have dubbed nuclear pasta, formations of spaghetti-like strands and lasagna-like sheets of matter that exist nowhere else in nature. The gravity on a neutron star is so intense, around 100 billion times that of Earth, that anything not part of the core structure is flattened instantly. Yet simulations suggest that these crusts can support surface deformations just a few millimeters tall. Due to the intense gravity, Even these tiny mountains may produce detectable ripples in spacetime, gravitational waves. This fact boggles the mind. A bump the size of a thumbnail on a neutron star could emit gravitational radiation measurable across the galaxy. These mountains aren't just geological features. They are cosmic instruments, plucking the strings of spacetime like fingers on a violin. With each spin, each rotation, they generate waves that spread outward, stretching and compressing the fabric of reality. The material that allows such mountains to exist is believed to be the strongest substance in the universe, nuclear matter in a crystalline lattice, 1 billion times stronger than steel. If a structure built of this material were transported to Earth, it would collapse under its own weight and obliterate everything nearby, simply because our laws of matter cannot contain its density. What forms these mountains? One possibility is that accretion of material from a companion star systems creates uneven deposits on the neutron star's surface. These irregularities resist flattening due to the incredible strength of the star's crust. Alternatively, crustal fractures or magnetar activity could also create persistent deformations. These are not features meant for observation with a telescope. They are sensed indirectly, through gravitational wave detectors like LIGO and Virgo. These instruments search the universe not for light, but for tremors, distortions in spacetime itself. If a neutron star has a mountain, and spins at high speed, it could broadcast a steady gravitational tone, a note without sound, traveling through the cosmos. We've only begun to listen. And the notes may already be playing. On Earth, we understand mountains as colossal, enduring monuments of geology. On a neutron star, a mountain barely rises above the surface, but its gravitational signature dwarfs Everest. It reminds us that scale is relative, and power is not always about size. Sometimes, the tiniest imperfection can carry the loudest voice. A mountain just a few millimeters tall, standing defiant against the crush of cosmic gravity, may be one of the most remarkable structures in the universe. And somewhere out there, it is singing. In the vast and ancient tapestry of the cosmos, one of the most profound discoveries came from studying what should have been nearly uniform: the cosmic microwave background, CMB, the residual glow from the Big Bang. It is a map of the early universe, a nearly perfect sphere of radiation, just a few degrees above absolute zero, imprinted on the sky. But hidden within this uniformity is an enigma, the cold spot. A region of the CMB, stretching nearly 1.8 billion light-years across, that is significantly colder than its surroundings. Not by a wide margin, just a few hundred microkelvin, but enough to cause scientists to pause, stare, and question the foundations of our cosmological model. The cold spot is real. It's been confirmed by multiple satellite missions, including NASA's WMAP and ESA's Planck. At first, scientists assumed it was just a statistical fluke, a natural blip in the random distribution of primordial energy. But over time, doubts grew. The region is colder than expected by more than 5 sigma, a statistical threshold significant enough to warrant deeper scrutiny. One hypothesis emerged: the cold spot could be caused by a supervoid, a massive region of space that contains far fewer galaxies, stars, and matter than average. If photons from the CMB pass through such a void, they might lose a tiny bit of energy due to a phenomenon called the integrated Sachs-Wolf effect. In essence, light gets stretched by the expanding universe as it travels through underdense space, causing it to cool slightly. Astronomers indeed found evidence of a void, a region lacking galaxies, in the direction of the cold spot. But it wasn't large enough. The void couldn't account for the full temperature anomaly. The data didn't match. The riddle remained. That's when things turned speculative. Some theorists proposed a collision with another universe. According to inflationary theory, our universe may be just one bubble in a much larger multiverse. In the earliest moments of existence, these bubbles might have collided. If so, such a collision could have left an imprint, a cosmic bruise, in our observable universe. The cold spot might be such a scar. It's a wild idea, one that tugs at the boundary between physics and philosophy. We have no direct evidence for other universes, and the multiverse remains a theoretical frontier. But the cold spot is one of the only places in the observable sky that might support the idea. Another possibility is that it's a sign of topological defects, relics of early universe phase transitions, like cosmic strings or textures. These exotic structures, if they exist, could distort space in subtle but measurable ways, leaving imprints like the cold spot. And yet, the most sobering interpretation remains that we don't know. That this patch of sky, colder than expected, is a statistical outlier, a cosmic coincidence. With trillions of galaxies and infinite potential patterns, some things will look strange. But in the coldness, wonder persists. For this region, this anomaly represents more than just temperature. It is a mirror, one that reflects our longing to understand, to explain, to connect the dots of our cosmos into meaning. Whether it's a void, a mirror universe, or a scar from creation itself, the cold spot invites us to keep looking. It sits on our cosmic map like a whisper. There is more. Red dwarfs are the silent workhorses of the universe. Small, dim, and cool, these stars account for over 70% of all stars in the Milky Way. They burn slowly. Some may live for trillions of years, outlasting the entire current age of the universe by a factor of 100. For decades, they were considered poor candidates for life-bearing planets. But now, they are among our most promising targets in the search for extraterrestrial life. Unlike stars like our Sun, red dwarfs emit most of their energy in the infrared spectrum. This means that planets orbiting close enough to receive warmth, within what's known as the habitable zone, must huddle much nearer to their star. Often, this leads to tidal locking, where one side of the planet always faces the star in endless daylight, and the other in eternal night. This configuration, once seen as hostile, now inspires fascination. Climate models suggest that if a planet has a thick enough atmosphere, rich in greenhouse gases like carbon dioxide, it can circulate heat from the day side to the night side. The result could be a habitable twilight band, a ring of perpetual dusk between day and night, where temperatures are stable and moderate. A permanent sunset world. The idea is haunting, a planet where the sun never rises nor sets, but hangs in the sky at a fixed angle, casting orange-red light across windswept plateaus and reflective oceans. Forests might grow in this twilight zone. Creatures could evolve to bask in constant warmth, or retreat into the colder regions to rest. But red dwarfs come with complications. In their youth, they are notoriously volatile, releasing intense flares of ultraviolet and X-ray radiation. These flares could strip atmospheres from nearby planets or sterilize their surfaces. Yet, over billions of years, these stars quiet down. If a planet can hold on through the tempest, it may enjoy unimaginable stability, a calm, unchanging climate for eons. Life, after all, is resilient. On Earth, we find organisms in boiling vents, arid deserts, and frigid Antarctic lakes. If evolution had trillions of years to work with, on a planet with steady conditions, the results could be extraordinary. Moreover, red dwarf systems are abundant and nearby. The closest star to us, Proxima Centauri, is a red dwarf, and it hosts a potentially rocky planet, Proxima b, within its habitable zone. The TRAPPIST-1 system, just 39 light-years away, has 7 Earth-sized planets, 3 of which may be habitable. It's entirely possible that the first signs of alien life we detect, be it biosignatures, oxygen atmospheres, or even radio signals, will come from a red dwarf system. In fact, they may already be watching us from their quiet, persistent vantage points. In the grand game of cosmic probability, longevity matters. And red dwarfs, with their billions upon billions of years, offer life not just a spark, but a legacy. In the icy corners of our solar system, far from the sun's warmth, lie some of the most promising locations for alien life. Not planets, but moons. Specifically, moons that hide liquid water oceans beneath thick shells of ice. These are worlds not warmed by sunlight, but by tidal forces and internal heating, turning frigid stones into cradles of possibility. 2 moons stand at the forefront of this hope: Europa, orbiting Jupiter, and Enceladus, orbiting Saturn. Beneath their frozen exteriors lie vast, global oceans, confirmed through gravitational measurements and magnetic field data. Europa's ice crust is cracked and streaked, like a shattered porcelain shell, suggesting motion beneath. Beneath that crust, a liquid ocean up to 100 kilometers deep may cover the entire moon. It's bombarded by Jupiter's radiation, but the ocean below is likely shielded, a dark, alien sea. Enceladus, though smaller, is perhaps even more dramatic. In 2005, NASA's Cassini spacecraft observed plumes of water vapor erupting from its south pole, geysers blasting hundreds of kilometers into space. These plumes contain water, salts, and organic compounds, hinting at complex chemistry beneath the surface. The source? A liquid water ocean heated by tidal friction, the push and pull of Saturn's gravity flexing the moon's interior, generating warmth. Enceladus is essentially a deep frozen shell covering a warm, salty ocean, possibly touching rock. And where water meets rock, hydrothermal vents could form, the same type of environment where life may have first arisen on Earth. These moons are not anomalies. Other candidates include Ganymede, Callisto, Titan, and Triton. Some of these may host oceans dozens of times deeper than Earth's, oceans with more water than all our seas combined. And if water is there, and heat is there, could life be far behind? We don't yet know. But we're preparing to find out. NASA's Europa Clipper mission, launching soon, will orbit and study Europa in detail, searching for signs of habitability and potential plumes. Meanwhile, future missions may sample Enceladus's geysers directly, looking for biosignatures, molecules that indicate life, or its remains. The exciting part is this: unlike Mars or exoplanets light years away, these oceans are reachable. We don't need to land. We may just need to fly through the mist of a geyser to discover alien biology. Imagine it, the first discovery of extraterrestrial life, not on a planet, not on a star, but in the hidden ocean of a moon, beneath a crust of ice, warmed by the invisible tug of gravity. In the end, it may be the coldest places in our solar system that prove the warmest to life. On August 15, 1977, at the Big Ear Radio Observatory in Ohio, a faint signal from the constellation Sagittarius lit up a narrowband radio receiver, and then vanished. The printout showed a burst of energy, lasting 72 seconds, with values so unusual that astronomer Jerry Emmons circled them in red and wrote one word in the margin: "Wow!" To this day, it remains one of the most tantalizing candidates for an extraterrestrial signal ever recorded. Not because of what it said, it didn't say anything. It wasn't modulated. It wasn't encoded. But because of what it wasn't. It wasn't from Earth, it wasn't from a satellite, and it didn't match any known natural phenomena. It came from somewhere between Sagittarius and Capricornus, near a group of stars too distant and dim to resolve individually. It lasted the exact length of the telescope's skin time, suggesting it was fixed in the sky, like a beacon or a broadcast. Then it never repeated again. What makes the wow? Signal remarkable is its frequency, 1420 MHz, the natural emission line of neutral hydrogen, the most abundant element in the universe. Astronomers have long speculated that intelligent civilizations might choose this frequency as a universal hailing channel. The hydrogen line is quiet, recognizable, and cosmically symbolic. And yet, nothing since. Thousands of radio observatories have scanned that same region of the sky, in the same band, and found nothing. No repeat. No echo. Just silence. Was it a hoax? Unlikely. The Big Ear's data stream was analog and monitored continuously. Was it interference? Tests ruled out known Earth-based sources. Could it be a cosmic anomaly, a rare natural radio burst? Possibly, but it lacked characteristics of pulsars, quasars, or fast radio bursts. Or was it real? A deliberate, narrow-band signal sent across the stars, caught briefly by chance, and never heard again? The implications are dizzying. If it was a message, it was not aimed at us. Earth just passed through its beam. Or perhaps it was a lighthouse, sweeping regularly across the galaxy, and we caught it during a single rotation. Some even speculate that the signal's non-repetition is the point. That advanced civilizations don't repeat themselves. Detection by hostile neighbors, a variation of the dark forest theory. In 2017, astronomers found a possible culprit. A comet, 266P/Christensen, was near the region during the detection. Comets can emit radio waves, and it was suggested that the signal may have originated there. But this explanation has been debated and is far from conclusive. To date, no hypothesis fully accounts for the WOW signal's strength, narrowness, and behavior. And so, it lingers, not as proof, but as possibility. A whisper in the static. A cosmic punctuation mark. And a perfect symbol for the paradox we inhabit, a galaxy filled with stars, planets, molecules, and yet no voice. The WOW signal remains a monument to curiosity. We heard something. It came from space. It defied easy answers. And in that brief pulse, we remembered how much we don't know. Perhaps one day it will return. For centuries, the solar system has been viewed as ours, a domain of lifeless planets, moons, and rock. But a provocative idea has gained traction in recent years. What if artifacts of alien technology already exist here, unnoticed, ancient, silent? This is the essence of the lurker hypothesis, that advanced civilizations, perhaps millions of years old, may plant autonomous probes in stellar systems to observe emerging life. These devices, passive and undetectable, could monitor, record, and transmit without revealing themselves. In 2011, the SETI Institute's Paul Davies proposed a bold idea: search the Lagrange points, gravitationally stable regions between Earth and the Moon, for potential alien artifacts. These points could host stationary objects indefinitely, orbiting quietly. The idea wasn't fantasy. It was a formal, peer-reviewed proposal. Others have suggested scanning the surface of the Moon, particularly its far side, where human eyes and instruments rarely gaze. An ancient probe could sit undisturbed for millions of years, eroded only by micrometeorites. The asteroid Oumuamua, which passed through the solar system in 2017, reignited these questions. Its hyperbolic trajectory, extreme elongation, and non-gravitational acceleration led some, notably Harvard's Avi Loeb, to suggest it could be a probe or light sail from another civilization. The mainstream rejected the idea, citing natural explanations. But the object's behavior remains inconclusive. What would alien probes look like? Not blinking lights or massive monoliths, but tiny, hardened, energy-efficient devices. Some might resemble rocks. Others could hide in plain sight as technosignature mimics, blending with asteroids or hiding in orbital debris. Could they be active? Possibly. But more likely they're passive, designed only to observe. Their creators may have long since gone extinct, or they may be watching still. Some theorists compare the situation to Amazonian tribes unaware of satellites above them. Civilizations on Earth may be advanced in their own right, but still utterly invisible to those passing above, scanning silently. If probes do exist, how would we find them? We'd look for anomalies, strange thermal signatures, unusual orbits, unnatural materials. We'd analyze decades of archival data, not for signals, but for structure. It's a different kind of SETI, one rooted in archaeology, not conversation. Critics argue the idea is speculative, and it is. But it's testable. We can scan Lagrange points. We can map lunar anomalies. We can revisit unexplained spacecraft flybys and gravitational oddities. And even if we find nothing, the search itself teaches us how to think differently, to look inward, not just outward. To consider that first contact might not arrive as a transmission, but as a discovery of an object, of a silence too deliberate. If alien probes exist in our system, they may already know us well. They may have watched the rise of agriculture, of radio, of rockets. They may have recorded our wars, our art, our sounds. And someday, perhaps, we'll find one. In 2014, astronomers witnessed something extraordinary. A star, designated IPTF-14HLS, underwent a supernova explosion, the violent death throe of a massive star. Fading into darkness, it stayed bright. For months. Then, a year later, it brightened again. And again. In total, this star exploded at least 5 times over 3 years, a behavior that defies every known model of stellar death. Normally, a supernova is a one-time event, a terminal flash. But IPTF-14HLS didn't go quietly. It flared, dimmed, reignited, as if it refused to die. Located about 500 million light-years away in the constellation Ursa Major, this celestial mystery pulsed with energy, emitting light equivalent to billions of suns. When researchers examined archival data, they discovered something even stranger, a similar outburst from the same region in 1954. Could it be the same star? Had it survived an earlier explosion, only to erupt again 60 years later? One theory involves pulsational parainstability supernovae, rare events in extremely massive stars. In such stars, the core becomes hot enough to convert high-energy gamma rays into matter-antimatter pairs, reducing the radiation pressure that supports the star. The result: a partial collapse followed by an explosive rebound, shedding vast layers of mass, but not destroying the core. The star survives. Temporarily. This could happen multiple times. Each eruption would resemble a supernova, but the star might persist, regenerating, until a final collapse. If this explanation is correct, IPTF-14HLS may be among the most massive stars ever observed, possibly over 100 solar masses at birth. Its repeated deaths mark a dance at the edge of physics, where nuclear forces struggle against gravity in a cosmic tug-of-war. But the truth remains unclear. Some suggest the phenomenon may involve a binary star system, or black hole feedback, or even exotic dark matter interactions. But none of these fully account for the light curves, energy, and timeline. More provocatively, some thinkers whisper about engineered stars, that what we're witnessing is not nature alone, but astroengineering on a stellar scale. Could an ancient civilization manipulate stellar collapse for energy, communication, or spectacle? Such ideas are speculative, but the sheer oddity of IPTF-14HLS invites wild questions. Today, the star has dimmed, But its memory lingers, a reminder that even in the most studied processes of astrophysics, surprises abound. That stars, once thought to follow predictable fates, may harbor hidden chapters. In the grand chronicle of cosmic life and death, IPTF 14HLS is an anomaly, a defiant spark, a star that staggered through multiple deaths, rewriting what it means to end. We often speak of supernovae as final. But maybe, just maybe, the universe allows for encore performances. In the heart of every atom lies a nucleus, a tight knot of protons and neutrons held together by the strong nuclear force. Most of the elements we know are stable, or decay slowly over time. But deep in the realm of theoretical physics lies a question: is anything truly eternal? Enter bismuth 209, long thought to be the heaviest stable isotope in the periodic table. For over a century, it was considered unchanging, indestructible. But in 2003, scientists finally measured its decay. Very, very slowly, a bismuth 209 nucleus transforms into thallium 205, releasing a faint alpha particle. The half-life? Approximately 1.9x10 superscript 2 years, over 1 billion times the current age of the universe. In essence, bismuth 209 is functionally immortal. And yet, not quite. It whispers a single truth: nothing lasts forever. This discovery leads to a chilling, poetic question: what happens to the universe when even the most stable particles begin to fall apart? According to some cosmological models, we are living in the stelliferous era, an epoch where stars shine, galaxies form, and life evolves. But trillions of years from now, the lights will go out. Stars will fade, black holes will evaporate, and only degenerate remnants will remain: white dwarfs, neutron stars, cold planets. Then begins the degenerate era, followed by the black hole era, and finally, the dark era. In this time, the universe is quiet, cold, still. The only events are quantum decays, actions, and the occasional glimmer of a rare fusion. It is in this darkness that atoms like bismuth 209 will continue to exist, slowly, inexorably changing. Their decay is the heartbeat of a dead universe, ticking on scales beyond comprehension. The final decay of all baryonic matter, the atoms we're made of, marks the true end of time. No more reactions. No more light. Only silence. But perhaps in this silence, there is something profound. To us, 13.8 billion years feels vast. But to bismuth 209, it's an eye blink. Its patience outlasts stars, civilizations, even the concept of history. It holds within its nucleus a promise of entropy, wrapped in unimaginable longevity. We marvel at galaxies and black holes, but this quiet nucleus, may be the last actor on the universal stage. And when it finally decays, the curtain falls. Roughly 340 light-years from Earth, orbiting a star much like our own, is a gas giant called WASP 12b, a world that defies our understanding of planetary physics. It's a planet so strange, so self-destructive, that it has earned the nickname the planet that eats itself. WASP 12b is a hot Jupiter, a massive gas planet, larger than Jupiter, that orbits its star in just over 1 Earth day. That's about 3 million kilometers from its star, dangerously close. At this proximity, the planet's day side is heated to over 2,500 degrees Celsius, hotter than some stars. But it's not just the heat that shocks scientists. WASP 12b is elongated, stretched by the star's gravity into an egg-like shape. This distortion is so extreme that its atmosphere is bleeding into space, forming a ring of gas that trails behind the planet. It is literally evaporating, a planet that is being torn apart and consumed by its host star. This process is happening on astronomical fast-forward. Within a few million years, a blink in cosmic time, the planet will be gone. Its material will have joined the star, its memory extinguished. But here's the puzzle: how did it get there? Giant planets are thought to form far from their stars, where icy materials can accumulate. Yet WASP 12b is in a furnace zone, too close for conventional formation theories. Did it migrate inward through gravitational interactions? Was it captured by its star? Or did some violent celestial event throw it into a death spiral? And how many others are like it? We've now discovered hundreds of hot Jupiters, all seemingly out of place. They orbit too close. Their atmospheres burn and shimmer. Some have metallic clouds, glass rain, or iron vapor. Some are being shredded. Others glow with their own internal heat. They are, by all accounts, planets that shouldn't exist, and yet they do. WASP 12b might be the most dramatic. Its host star is consuming its atmosphere, detectable as changes in starlight as the gas cloud moves across it. In fact, the star itself is dimming faster than expected, perhaps due to the accumulation of planetary matter, a celestial cannibalism playing out in real time. Even stranger, some researchers speculate that WASP 12b may be a precursor to a future Earth-like world. That once enough mass is stripped, a rocky core could remain, orbiting close, scorched and bare, the ashes of a former giant. In this, WASP 12b becomes a cosmic metaphor, that even the largest, most powerful structures are not immune to destruction. That planets, like stars, have life cycles. And that sometimes, the very thing that gave them light will also take it away. The universe is not only vast, it is profoundly dynamic. WASP 12b teaches us that some worlds burn twice, once in their formation, and again in their unraveling. And perhaps, in that final spiral into the star, there is a quiet beauty. A world giving itself back to the cosmos, particle by particle, breath by burning breath. ChatGPT. Beneath the frozen crust of Titan, Saturn's largest moon, lies a world stranger than science fiction. A place where oceans exist without light, where rivers flow without water, and where an entire atmosphere dances above a subterranean sea. Titan is the second largest moon in the solar system, larger even than Mercury. The other moon, it has a thick atmosphere, composed mostly of nitrogen, with traces of methane and hydrocarbons. It's the only moon with weather, clouds, rain, and seasons. But none of this involves water. Here, methane takes water's role. It evaporates, forms clouds, rains down, and carves valleys. There are lakes, seas, and storms, all made of liquid methane and ethane. Radar images from the Cassini mission revealed entire coastlines, river deltas, and shifting seasonal weather patterns. But that's just the surface. Beneath Titan's icy crust, which may be dozens of kilometers thick, lies something even more profound, a global subsurface ocean of liquid water, likely mixed with ammonia to keep it from freezing. It's vast, salty, and under pressure, a hidden ocean beneath an alien sky. This makes Titan one of the most promising places to search for extraterrestrial life. Not life like ours, not plants or fish or forests, but extremophiles, microbial organisms adapted to dark, cold oceans beneath miles of ice. Even more intriguing, Titan's chemistry is prebiotic. Its atmosphere is rich in complex organic molecules. UV radiation from the sun drives reactions in the upper layers, forming compounds like hydrogen cyanide and acetylene, potential building blocks for life. On Earth, these molecules would dissolve in water and begin forming more complex chains. On Titan, they might sink through the icy surface, entering the underground ocean. There, in darkness, something new might emerge, something unfamiliar, perhaps even non-carbon based. NASA plans to investigate this mystery with Dragonfly, a rotorcraft lander launching in the 2030s. It will fly across Titan's diverse terrain, sampling soil, atmosphere, and chemistry. It won't just search for life, it will search for the conditions of life. Titan is also one of the most Earth-like bodies we've found, not because it's warm, or blue, or bright, but because it's complex. It has weather, geology, liquid cycles, and seasons. It has energy, chemistry, and time. It is a system, not a rock. And it forces us to ask, what is a world? Is it only a place with warmth and oceans like ours? Or could it be a methane coast beneath an orange sky, with tides pulled by Saturn, and clouds made of hydrocarbons? In Titan, we glimpse an alien Earth. One frozen, reversed, and slowed, but no less alive in its motion. In the distant halo of the Milky Way, a strange traveler hurtles through space, a hypervelocity star, moving so fast it defies gravitational bounds. But this star is more than just fast. It may be from another galaxy entirely, a living relic of a cosmic collision. Meet Hio 437 to 5439, a young blue, massive star located about 200,000 light-years from Earth. It's racing away from the galactic center at over 700 kilometers per second, so fast that it's on track to escape the Milky Way forever. This is strange. Young stars like this shouldn't exist out there. They form in galactic disks, not in halos. So where did it come from? The initial theory was that it was ejected from the Milky Way, perhaps flung by the massive gravitational slingshot of our central black hole. But He 04375439 is too young. It would have died before making the trip. Unless, of course, it came from somewhere else. Astronomers began to trace its trajectory and found something astonishing. The star's path may intersect with the Large Magellanic Cloud, LMC, a satellite galaxy orbiting the Milky Way. If Hio 437 to 5439 was born there, its speed and age suddenly make sense. But how did it achieve such velocity? One theory suggests that in the LMC's dense core, a triple-star system interacted with a massive black hole. In this gravitational melee, one star was captured, and another was ejected, violently flung into intergalactic space, becoming a runaway star. This means Hio 437 to 5439 isn't just fast, it's a galactic refugee, a messenger from another world. It carries with it the chemistry and history of a foreign galaxy, offering a unique glimpse into alien stellar evolution. But it's not alone. We've now detected several hypervelocity stars, some heading into the Milky Way. Trajectories. Each one is a puzzle, a particle of cosmic violence, ejected by black holes, stellar mergers, or unknown forces. These stars challenge our maps. They remind us that galaxies are not isolated. They collide, merge, and fling matter across millions of light years. And in these events, stars become wanderers, tracing arcs of unimaginable age. Perhaps some of these travelers carry planets, or even dead civilizations, long frozen worlds, orbiting rogue stars on intergalactic journeys. Perhaps the silence of space is broken only by motion, by objects in transit. And perhaps, somewhere out there, an alien astronomer is watching our sun, not because it's special, but because it, too, is part of a migrating galaxy, filled with strays. Hio 437 to 5439 is not just a star. It's a witness. To collision. To motion. To the idea that the sky we see is not local, but stitched from countless pasts. It moves still, into the void, bright and burning, alone. In a distant corner of our galaxy, nearly 1,300 light-years from Earth, there is a world so unusual, it would make science fiction writers blush. Its name is KOI 5ab, and it orbits not one, not two, but 3 stars. For centuries, humans have imagined twin sun planets, like Tatooine from Star Wars, with double sunsets and binary skies. But KOI-5 makes even that seem tame. This planet is part of a triple star system, where 3 stars orbit a shared gravitational center. The system itself is locked in a kind of cosmic ballet, with orbits within orbits, and light from 3 different sources bathing the planet in complex rhythms. Here's how it works. KOI-5 orbits 1 star. Let's call it Star A. That star is closely bound to a second star, Star B, in a tight binary orbit. A third star, Star C, orbits the A, B pair from farther out. So KOI-5's parent star is in a double dance while being watched from afar by a distant third partner. The result? A planet that is constantly tugged and torqued by shifting stellar gravities. Its seasons and day-night cycles would be erratic, unstable. Sunrises from multiple points. Eclipses that follow no simple pattern. And a sky filled with multiple shadows, hues, and directions of light. KOI-5 itself is a gas giant, large and heavy, similar to Saturn or Jupiter. It was first discovered by NASA's Kepler mission in 2009, but it was ignored for over a decade. Why? Because its light curve, the way its transit dims the star, was too messy, too strange. The data didn't fit. It wasn't until much later, with the help of other telescopes like TESS and Keck, that astronomers confirmed its existence and realized this planet orbits in a place that shouldn't work. The odds of a stable orbit in a triple star system are slim. Gravitational disturbances usually eject planets, or prevent them from forming at all. KOI-5 somehow survived. Or maybe it migrated. Some researchers speculate the planet may have formed farther out and moved inward later. Others wonder whether the third star perturbed its orbit into its current position. Either way, KOI-5's presence is a riddle, a survivor in a gravitational storm. What would life be like under 3 suns? Could a moon of KOI-5 be habitable, warmed by triple sunlight and subject to wild tides and magnetic fields? The possibilities are dizzying. This system also expands our definition of a normal solar system. Our own, with a single sun and neatly spaced planets, may be an outlier. The more we explore, the more we realize the cosmos prefers complexity, messiness, surprise. KOI-5 orbits in defiance. It thrives in chaos. It tells us that even in hostile conditions, stability can emerge, and perhaps, so can life. In the sky of KOI-5, shadows would fall in 3 directions. Night might never come fully, and a single eclipse could turn the world dark with 3 strokes. Dark matter, the invisible scaffolding of the universe. It makes up 85% of the matter in the cosmos. We don't see it, but we know it's there from its gravitational pull. Without it, galaxies shouldn't form, stars shouldn't orbit, and the universe wouldn't hold together. NGC 1052 DF2, a galaxy that appears to have no dark matter at all. Discovered in 2018, this faint, diffuse galaxy stunned astronomers. Its stars are loosely bound, spread over a vast area. Its mass, measured by tracking the motion of star clusters, is almost entirely explained by the visible matter alone. There's no hidden mass. No unseen halo. No dark matter. This wasn't just rare. It was unthinkable. How can a galaxy exist without dark matter? And if one galaxy can do it, what does that mean for the theory that dark matter is necessary? There are several possibilities, none fully satisfying. One idea is that DF2 formed in a galactic collision, where gas was stripped and reassembled into a new galaxy without bringing dark matter along. But simulations show this is hard to pull off. Another theory suggests it's a tidal remnant, the leftover of a disrupted dwarf galaxy, but that too struggles to explain the full picture. Then came DF4, a second galaxy nearby, with similar properties. Suddenly, it wasn't just a fluke. Something is happening in this region of space that challenges our understanding. Some physicists saw in DF2 and DF4 a potential crack in the dark matter paradigm. If dark matter doesn't exist everywhere, maybe it doesn't exist at all? Perhaps the effects we attribute to dark matter are the result of modified gravity or unknown laws. But others urge caution. Maybe DF2 is just weird. Maybe dark matter is still there, but in forms we can't detect. Or maybe our measurements are incomplete. Regardless, the galaxy stands as a cosmic contradiction. A thing that shouldn't be yet is. And it reminds us, dark matter, for all its explanatory power, is still a placeholder. A name for something we don't understand. We can't see it. We don't know what it's made of. It doesn't interact with light, or electromagnetism, or chemistry. Only gravity. So when gravity fails to act as expected, when a galaxy moves in ways that don't require dark matter, we're left staring into a cosmic mirror, asking, what else don't we know? NGC 1052 DF2 is a ghost, a whisper, a rebuttal to certainty. Whether it rewrites physics or merely deepens the mystery, it reminds us of the universe's favorite trick, surprise. In the constellation Cassiopeia, nearly 40 million light-years from Earth, lies a stellar enigma that has baffled astronomers since 2009. A massive star, the kind that should have ended in a spectacular supernova, simply vanished. This star, known as SN 2009 IP, had shown all the signs of imminent death. It was enormous, a luminous blue variable, 50 to 80 times the mass of the Sun. Over years of observation, it flared repeatedly, shedding material in violent outbursts. In 2012, it brightened dramatically. Telescopes around the world watched, expecting the final, colossal detonation, a true supernova. But that didn't happen. The brightness faded. The star seemed to stabilize. No expanding debris cloud. No telltale radioactive elements. It dimmed, but not into darkness. It didn't die. It didn't survive. It entered a twilight state, flickering, unstable, undead. Some astronomers believe SN 2009 IP did explode, but in a failed supernova, where the core collapses directly into a black hole without a bright outburst. Others suggest it experienced a massive outburst, mimicking a supernova but leaving the star intact. A third possibility, it merged with a hidden companion in a stellar collision, causing a pseudo-supernova flash. Yet none of these explanations fully satisfy the data. Even weirder, SN 2009 IP is not alone. Several other zombie stars have been spotted, massive stars that flare violently, appear to die, and then linger. They sit at the edge of known stellar evolution, not alive, not dead, but something in between. What happens in these liminal moments? Stars are not singular objects. They are processes, ongoing battles between gravity and pressure, heat and collapse. As their fuel runs out, their cores teeter on thresholds, some tipping into explosions, others into black holes, and some into this. A cosmic limbo. It may be that under certain conditions, extreme mass loss. Rotational velocity. A star doesn't end cleanly. Instead, it stumbles. It ejects part of itself, regains balance, falters again. Its death is not an event, but a process spread across decades. And in those decades, telescopes on Earth watch, waiting for the final silence. SN 2009 IP is a reminder that even the most powerful things in the universe can hesitate. That death is not always immediate, and that in the space between endings, something new might emerge. A failed supernova? A slow collapse into darkness? Or a rebirth? We do not know. But in the faint glow of that distant star, we glimpse the beauty of uncertainty. and the quiet defiance of a cosmos that refuses to behave. Somewhere in the constellation Vela, 1,300 light-years from Earth, lies a star that acts like a cosmic lighthouse, pulsing with a regularity so precise, it could keep time better than an atomic clock. This is a pulsar, a spinning neutron star, the dense remnant of a supernova. But this one, known as PSR J0941-4046, doesn't behave like any we've seen before. It blinks, and then goes silent. It pulses in radio waves for about 300 seconds, and then nothing. No signal. No radiation. For up to an hour, it disappears completely. Then, just as suddenly, it resumes. This behavior was so strange that astronomers thought it might be a telescope error, or terrestrial interference. But repeated observations confirmed it. This star is a long-period radio transient, one of only a few ever discovered. What could cause this? The answer may lie in magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These magnetic monsters twist space and time around them. Some theorists believe J0941-4046 could be a magnetar, pulsar hybrid, flipping between states as magnetic stresses build and release. Or perhaps it's entering a phase of stellar death we've never observed. As it cools, its magnetic field might be decaying, its pulses faltering. We may be watching the last heartbeat of a dying star. But there's another possibility. The pulses themselves are incredibly regular when present. This suggests not chaos, but structure. Some scientists have even proposed that these kinds of signals, if found repeating across regions, could resemble alien beacons. Not because they are, but because they mimic the kind of periodicity we might expect from intentional transmissions. We're not saying this is alien, but we are saying, if an alien civilization wanted to announce itself, this is what it might look like. PSR J0941-4046 reminds us that even the dead can speak. That the remnants of stars can reach across light years with messages, real or metaphorical, encoded in rhythm. It is a whisper from a collapsed sun. A rhythm so precise, so haunting, that it transcends explanation. And somewhere, in the gaps between pulses, we feel the tension of the unknown. A signal that starts, stops, returns, like a breath, like a thought, like a message we haven't yet learned how to read. In the growing catalog of exoplanets, one kind continues to baffle scientists more than any other: hot Jupiters. These are gas giants, often larger than Jupiter, that orbit extremely close to their parent stars, sometimes completing a full orbit in just a few Earth days. At that proximity, the planets are scorched, their atmospheres blasted by stellar radiation, and their orbits so tight that they seem to defy the rules of planetary formation. According to current models, giant planets like Jupiter form in the outer regions of a star system, beyond what's called the frost line, where it's cold enough for ices to condense and build up mass. So how did these hot Jupiters end up so close to their stars? There are two main ideas. One is migration, that the planets formed farther out and moved inward over time, shepherded by gravitational interactions with disks of gas or other planets. The second is scattering, where gravitational battles between planets fling one inward and the other outward. But neither theory fully explains the strangest cases. Some hot Jupiters orbit so close that their atmospheres are literally boiling off, like tails of gas trailing behind them. Others have orbits that are tilted, or even retrograde, moving in the opposite direction from their star's rotation, a configuration that shouldn't happen unless violent disruptions occurred. Then there are planets like WASP 12b, where the orbit is decaying so rapidly that the planet will be swallowed by its star in just a few million years. Or KLT 9b, which is heated to over 4,000 degrees Celsius, hotter than some stars, and may be losing hundreds of tons of atmosphere every second. Why do these planets even exist, if they are so unstable and short-lived? It could be that we are seeing a transient population, the brief final phase of planetary life before destruction. Or perhaps our models of formation and migration are incomplete, missing mechanisms that allow for such extreme worlds to emerge and survive. Another possibility is that hot Jupiters represent a kind of planetary evolution, a stage that many systems pass through but few remain in for long. They are a warning that our solar system is not typical. That planets can move, burn, collapse, and die in ways we never imagined. And they are a reminder that the universe doesn't care about our theories. It only cares about what works, for a moment, for a million years, or for as long as we can see it. In the sky of a hot Jupiter, the star never sets. The planet is tidally locked, one side forever scorched, the other in eternal night. And between them, in the thin ribbon of twilight, may lie winds moving faster than sound, and questions no model can yet answer. The cosmos is full of spirals, galaxies that whirl like giant pinwheels across the night. Most spiral galaxies, including our own Milky Way, share a common handedness, or spin direction, based on their orientation and the angular momentum they inherited from the early universe. But in 2008, the Sloan Digital Sky Survey revealed something strange. A small but significant number of spiral galaxies appeared to spin the wrong way. These galaxies, known as left-handed spirals, challenge the assumption that the universe is isotropic, the same in all directions. In fact, their distribution seemed to show a dipole asymmetry, more right-handed spirals in one half of the sky, and more left-handed in the other. If true, this would mean the universe has a preferred direction, something fundamentally forbidden by the cosmological principle, the idea that the universe is the same everywhere on large scales. The data was controversial. Some said it was a statistical fluke. Others argued that bias and telescope orientation might have affected the results. But then came follow-up studies using Galaxy Zoo, a citizen science project where volunteers classified over 1 million galaxies by shape. The asymmetry persisted. Not huge, just a few percent, but enough to raise eyebrows. If the spin distribution of galaxies is truly uneven, what could cause it? One theory involves primordial quantum fluctuations in the early universe that somehow seeded angular momentum in a non-random way. Another posits that a large-scale anisotropy in space-time itself, perhaps left over from cosmic inflation, could have tilted the formation of structure. There are even wilder ideas. What if the asymmetry is a shadow of a parallel universe, interacting with ours only through gravity? Or what if it's a signal, an artifact of design? Most physicists reject these interpretations as speculative. But the data lingers. Galaxies, after all, are not static. They spin, merge, tear, and reform. Their angular momentum can change. Yet when you see a billion light-year region of space with a favored twist, it's hard not to wonder, is the universe itself twisted? Are we living inside a rotating cosmos, too vast for us to feel, but not too vast to see? And if so, what lies in the other direction? In the night sky, spirals turn in silence. Some to the right, some to the left. Each a fingerprint of cosmic motion, and perhaps of something deeper. ChatGPT, imagine a solar system much like our own, a central star, surrounded by orbiting planets, possibly with moons and atmospheres. Imagine that star growing old, swelling in size, and reaching out with invisible hands of gravity and plasma to drag its children back into its burning belly. This is not myth. This is what happens when stars devour their planets. In 2023, astronomers witnessed, for the first time, a star consuming a planet in real time. The event occurred in our Milky Way, around a star about 12,000 light-years away. Using the Zwicky Transit Facility, researchers spotted a strange brightening, not a nova, not a flare, but something new. Follow-up observations with infrared telescopes revealed the truth. A planet at least the size of Jupiter had spiraled into its dying sun, triggering an outburst of energy as it was swallowed whole. This was the stellar equivalent of an elderly monarch eating its heir. As stars like our Sun age, they expand into red giants, growing hundreds of times their original size. Inner planets are consumed, their matter accreting onto the star's outer layers. The result is a violent flare-up of brightness and heat, and then silence. Evidence for such events has existed for years. Anomalous chemical signatures in stars, high metallicity in atmospheres, debris disks made of planetary remains. But to actually see it happen, with light curves and spectra, was a milestone. And the implications are vast. It suggests that many stars, perhaps even our own Sun in 5 billion years, will consume their planets. Mercury and Venus are already doomed. Earth may be as well. Simulations show that as the Sun expands, its outer layers may drag Earth inward, dooming it to a fiery fate. But it's not just about destruction. These events can lead to secondary phenomena, bursts of new radiation, altered stellar evolution, and even the creation of strange chemical elements from the fusion of planetary cores. Some stars, like BD plus 48740, show high lithium levels, a clue that something unusual happened, since lithium usually gets destroyed in stellar interiors. The likely cause? A swallowed planet. There are even theories that some peculiar types of stars, like blue stragglers, may have originated from planetary or stellar consumption. And in the violent end, we see echoes of beginnings. Planets form from the debris of stars. And in the end, they return, a loop of matter, light, and fire. To watch a star eat a planet is to watch time fold in on itself. It is a warning, a marvel, and a reminder that in the cosmos, nothing is safe from gravity, not even the worlds it once nurtured. In the darkness between large galactic clusters, where intergalactic space stretches seemingly empty, astronomers once believed there were few surprises. The great cosmic web of matter was thought to flow in strands and nodes, with voids in between, low in density, uneventful. And then we found DF44. Dragonfly 44 is a galaxy discovered in 2016 that defied nearly every expectation. It is a dark galaxy, a ghost-like object the size of the Milky Way but with only 1% as many stars. Its light is so faint that it was invisible for decades, hiding in plain sight. But the real shock wasn't its dimness, it was its mass. When astronomers measured the motions of its stars and the dispersion of light, they realized DF44 had the same gravitational mass as the Milky Way, but almost no visible matter. That means over 99% of its mass is dark matter. It is a galaxy made almost entirely of shadow. The discovery shook our understanding of galaxy formation. How can something so massive have formed without forming stars? Why did the gas not collapse into bright stellar nurseries? Some think DF44 began as a normal galaxy, but was stripped of its gas and stars by a collision or tidal interaction, leaving only its dark skeleton behind. Others believe it formed in isolation, under conditions that prevented star formation from ever igniting. DF44 belongs to a strange class known as ultra-diffuse galaxies, UDGs, objects so faint and spread out that they challenge telescope sensitivity. Hundreds have now been found, floating like ghosts between clusters, haunting the cosmic web. They may be remnants of failed galaxies, or the descendants of ancient interactions that alternate pathways for cosmic structure to arise. One theory posits that in the early universe, some regions formed dense halos of dark matter, but were flooded by cosmic radiation before stars could ignite. These halos lingered, cold and dim, never lighting up, invisible except through gravity. DF-44 is the loudest of these whispers. Its very existence is a message that we are blind to most of what the universe contains. That mass and light are not the same. That galaxies can exist in forms so delicate, so ghostly, they almost don't exist at all. And yet DF-44 is there. Real. Measurable. A galaxy that glows like the dying embers of a fire never fully lit. If galaxies are cities in the night sky, DF-44 is a silent ruin, a metropolis of dark matter, without windows, without streetlights, without voices. And it spins still, around the heart of silence. ChatGPT. High above the clouds of the exoplanet HD 189733b, it rains sideways. Not water, not methane, but glass, sharp, jagged shards of silicate glass driven by winds blowing at over 5,400 miles per hour. This is not fiction. HD 189733b is a gas giant located 64 light-years from Earth. Discovered in 2005, it quickly became a favorite of astronomers due to its proximity and transiting behavior, allowing for detailed atmospheric measurements. And what they found was otherworldly. Using instruments like the Hubble Space Telescope and Spitzer, scientists studied the planet's light during transits and eclipses. The spectra revealed silicate particles suspended in the atmosphere, the raw material for glass. Combined with extreme temperatures exceeding 1,000 degrees Celsius and violent global winds, the result is a weather system unlike any on Earth. Bladed particles of molten glass whip sideways at supersonic speeds. And that's only the beginning. HD 189733b is deep blue in color, but not due to water. Its hue comes from the scattering of light off the glass particles in its atmosphere. A world as beautiful as it is deadly. The planet is tidally locked, meaning one side perpetually faces its star, while the other is shrouded in night. The contrast drives extreme wind currents, creating a dynamic system that constantly hurls heat, particles, and energy across the planet. This discovery forced scientists to reconsider the limits of exoplanetary weather. Glass rain is not merely an exotic detail, it's evidence of chemistries and climates that challenge our assumptions. Other exoplanets show signs of iron rain, lava oceans, and even snow made of titanium dioxide. The universe's imagination far exceeds our own. And yet, the storm of glass on HD 189733b stands out. Perhaps it's the contrast, the sapphire beauty hiding a lethal atmosphere. Or the poetry of it, a world where it rains knives through skies the color of deep oceans. To live there would be impossible. But to imagine it, to realize such places exist, is to expand the limits of our cosmic awareness. It is a reminder that alien does not always mean alive. Sometimes the strangest worlds are those forged only by physics, chemistry, and impossible weather. And in those rains of shattered light, we glimpse a kind of elegance that no life could survive, but only wonder could love. In 2019, something extraordinary swept through our solar system, a comet with an orbit so extreme, so hyperbolic, that it could only have come from another star system. Its name was 2I/Borisov. It was the second known interstellar object to pass through our solar neighborhood, after the infamous Oumuamua. But Borisov was different. It looked and behaved like a classic comet, a nucleus of dust and ice, a coma, and a tail. But its trajectory was unmistakably alien. It was moving too fast on a curved arc that no solar gravity could capture. It was just passing through. For the first time in human history, we could study a comet born around another sun. Borisov's chemical makeup was both familiar and strange. It contained cyanide, carbon monoxide, and water ice, similar to solar comets, but with ratios and isotopes that didn't quite match. This suggests that the processes of comet formation may be universal, that across the galaxy form in the same way, delivering the seeds of molecules wherever they go. But there's a deeper implication. Comets like Borisov could be vehicles of panspermia, carriers of prebiotic compounds, ejected from one system, traveling for millions of years, and eventually crossing paths with another star. Perhaps Borisov passed near a young Earth-like planet in another system long ago, brushing it with organic compounds. And now, it passed near ours, a galactic message in molecular form. Even more intriguing, Borisov appeared to be more pristine than most local comets. Its dust particles were unusually small, and its fragmentation near the Sun suggested it had never been close to a star before. It was a virgin comet, untouched by heat, a time capsule from a distant past. Where did it come from? We may never know. Its path suggests an origin in the direction of Cassiopeia, but the galaxy is vast. It may have wandered for billions of years, ejected during the chaotic early life of a distant solar system. And after a brief visit, a flash of light in our telescopes, it was gone. 2I/Borisov reminds us that space is not a barrier. It is a bridge. Across the stars, rocks and ice move in silence, carrying the fingerprints of alien chemistry, the possibility of shared origins. A comet is not just an object. It is a question in motion. And sometimes, the answer is simply, we are not alone in how we are made. Our moon, familiar and silent, is not a perfect sphere. It is slightly flattened, with a bulging equator and uneven crust. But more interestingly, it wobbles, a phenomenon known as lunar libration. This wobble is what allows us to see 59% of the moon's surface over time, rather than just 50%. It rocks slightly back and forth, as if nodding to Earth. But recently, scientists have discovered that this wobble, once thought to be simple and stable, may have far-reaching consequences. In 2021, NASA released a study showing that the moon's orbital wobble, which follows an 18.6-year cycle, can amplify tides on Earth. When aligned with sea level rise, this could lead to dramatic increases in coastal flooding across the globe in coming decades. But there's more. Some researchers have found irregularities in the moon's rotation that suggest past impacts, or even internal asymmetries, possibly tied to a lopsided core or fossilized gravitational influences from when it was still molten. The moon's gravitational grip on Earth stabilizes our tilt and seasons. But over long timescales, its own behavior may change, slowly, subtly, in ways we are only beginning to understand. There are even mysteries beneath its surface. Using data from Grail, scientists have found mass concentrations, or mascons, hidden beneath lunar basins. These dense regions warp gravity locally, and may be relics of asteroid strikes or primordial formations. They affect not only orbiters but also the moon's tidal response to Earth's pull. And then there's the question of the far side, once thought geologically dead, now known to host strange magnetic anomalies and unexpected thermal patterns. The moon is not just a passive rock. It is active, dynamic in subtle ways. Its wobble is a symptom of deeper motion, the slow evolution of a satellite that has danced with Earth for billions of years. One day, long in the future, the moon will drift away from us. Already, it recedes by about 3.8 centimeters per year. Eventually, eclipses will end. Tides will weaken. Earth's axis may begin to wobble. But for now, we live in a rare window, a time when the moon fits the sun just right, when its gravity shapes our seas, and when its subtle nod keeps time with the Earth. A reminder that even the most familiar things are still in motion. Orbiting a star 320 light-years away in the constellation Auriga is an exoplanet called WASP-107b, a world that defies expectation not through its violence or extremes, but through its profound softness. This planet is as large as Jupiter, yet has only about 1/10 of Jupiter's mass. Its density is so low, it's been likened to cotton candy. If placed in water, were that physically possible? This fluffy world stunned astronomers when it was discovered, forcing them to reconsider the limits of planetary structure. How can something so large be so light? WASP 107b likely has a tiny solid core surrounded by a vast envelope of hydrogen and helium. Its low density suggests it never underwent the kind of violent heating or compaction common in gas giants. It likely formed far from its star, in a cool region, and then migrated inward. Today, it orbits its host star at just 1/8 the distance between Mercury and the Sun, making its outer layers swell in the star's heat, like a balloon left in the sun. This puffiness is more than a curiosity. It has consequences. It makes WASP 107b a perfect target for atmospheric studies. Light from its star filters through the expanded atmosphere, revealing traces of methane, water vapor, and possibly hydrocarbons, offering a laboratory for the study of gas chemistry beyond Earth. It also raises profound questions. Are there entire classes of planets we've missed, simply because they're too diffuse to block light during transits? Could such low-density planets host moons? Could they exist at different sizes, or even become free-floating after shedding their outer envelopes? In some models, a planet like WASP 107b might eventually be stripped bare by its star, leaving behind a hot, rocky core, a kind of planetary skeleton, exposed and glowing. Or, perhaps, it will remain as it is for billions of years, a silent gas balloon, drifting around its sun, too light to collapse, too gentle to fight. It reminds us that strangeness isn't always violent. Sometimes it floats. In the story of Tatooine from Star Wars, a young hero looks out at twin suns in the sky. For years, this was science fiction, a poetic metaphor for duality. But then, we found planets with 2 stars. And then we found one with 3. GW Orionis, a star system 1,300 light-years away, contains 3 stars bound in a complex gravitational dance. Around them is a massive, misaligned protoplanetary disk, a warped halo of gas and dust torn by the star's competing gravity. Within that disk, astronomers now believe a planet may be forming, a planet that would orbit all 3 stars. This isn't just rare. It's cosmically bizarre. Simulations suggest that the planet's orbit would be stable, moving in a wide ellipse around the chaotic inner trio. But the geometry is strange. The disk is twisted like a croissant, tilted across multiple planes. No known planet orbits anything like this. We are witnessing planet formation in an environment never thought possible. The system challenges what we thought we knew about gravity, disks, and collapse. It suggests that planet formation is incredibly resilient, capable of adapting to wild forces and complex configurations. What would it be like to stand on such a world? The sky would be a theater of motion, 3 suns rising and setting in complex rhythms. At times, all 3 might align, casting triple shadows. At others, 2 suns might set while one lingers. Nights would be rare and flickering. If life evolved there, its circadian rhythm might not be 24 hours, but some intricate loop of stellar dance. More than that, it suggests that our solar system may be the exception, not the rule. Binary and trinary systems are common. Disks can warp. Gravity can negotiate. And planets, fragile, stubborn things, can emerge even from chaos. GW Orionis is a lesson in complexity, a reminder that the cosmos does not follow our rules. It invents its own. Stars are born spinning. From the collapse of rotating clouds of gas and dust, Angular momentum ensures that most stars rotate rapidly in their youth, some spinning on their axis in mere hours. Over time, magnetic braking and stellar winds slow them down, but never completely. Even ancient stars retain some spin, except one. In 2022, scientists discovered HD 191612, a star that rotates once every 538 days, by far the slowest massive star ever recorded. This would be like Jupiter taking over a year to complete a single turn. What could cause such dramatic braking? The answer lies in magnetic fields and mystery. 91612 possesses a magnetic field over 10,000 times stronger than Earth's. This intense magnetism interacts with stellar winds, acting like a cosmic parachute, draining angular momentum over millions of years. But even that doesn't fully explain the dramatic slowdown. Some theories suggest the star once had a binary partner or even a planetary engulfment that altered its rotation. Others think it formed with an unusually low angular momentum from the start, a fluke of cosmic physics. What makes HD 191612 particularly strange is that it's not small or elderly. It's a massive O-type star, burning hot and bright, far younger than our Sun. Yet it spins more slowly than most ancient red giants. This could change how we understand the life cycles of massive stars. Spin affects fusion rates, mass loss, and even how stars die. A slower star may go supernova differently, collapse into a different kind of black hole, or emit different gravitational waves. HD 191612 may be the prototype of an entirely new class of stellar behavior, or a rare fossil of star formation gone strange. It's also a reminder that in a universe of motion, stillness can be just as shocking. A star that barely turns, burning, massive, yet quiet in its rotation, is like a cosmic clock that lost its pendulum. And yet, it keeps ticking. For decades, dark matter has been the invisible backbone of the universe. Galaxies spin too fast for their visible mass. They should fly apart, unless something unseen is holding them together. Dark matter explains that. Or so we thought. In 2018, astronomers found NGC 1052 DF2, a galaxy that appears to contain almost no dark matter at all. This wasn't just unexpected. It was heretical. Located about 65 million light-years away, DF2 is an ultra-diffuse galaxy, large, faint, and filled with sparse, old stars. When researchers measured the motion of globular clusters within it, tightly bound groups of stars, they expected to find rapid motion indicating a strong gravitational pull from dark matter. Instead, they found the opposite. The stars moved exactly as predicted by their visible mass. No extra gravity. No hidden matter. Just the light, and what the light implied. How could this be? Some theories suggest the F2 may have lost its dark matter during a galactic collision or interaction. Others propose it formed in a region of space where dark matter was unusually sparse. A more radical idea is that our understanding of gravity itself might be incomplete at cosmic scales. Then, in 2020, astronomers found a second galaxy, DF4, with similarly low dark matter content, bolstering the idea that these are not flukes. The implications are staggering. If galaxies can form without dark matter, then dark matter is not essential to galaxy formation. That challenges the standard cosmological model, or at least suggests it's more flexible than we imagined. It also opens the door to new physics, models of modified gravity, alternate forms of matter, or unknown interactions in the early universe. Some scientists now use these dark matter deficient galaxies as laboratories. They isolate variables, test gravitational behavior, and probe the architecture of the cosmos without the usual scaffolding. It's like stripping a building down to its beams, and realizing the blueprints don't quite fit. DF2 and DF4 are elegant in their defiance, silent reminders that even our most foundational beliefs are subject to change. In a universe held together by the invisible, sometimes, it's the exceptions that teach us the most. Black holes are usually born from massive stars, stellar giants many times heavier than our Sun. When such a star collapses, it leaves behind a black hole with a typical mass of 5 to 15 solar masses. That's the theory. But in 2019, astronomers found a black hole in the Milky Way with a mass of 70 times the mass of the Sun. They named it LB1. And it shouldn't exist. According to current models, stars in our galaxy should not be able to form black holes that massive. They would lose too much mass through winds and radiation during their lifetimes. A black hole of 70 solar masses was thought to require low metallicity stars, ancient stars with little heavy element content, and early galaxies. But LB1 is local. Its presence upended stellar evolution theory. Some astronomers speculated that LB1 might not be a single black hole, but a binary pair, or that we had misunderstood its orbiting companion and therefore miscalculated the mass. Others suggested exotic origins, direct collapse without a supernova, or even primordial black holes, relics of the early universe, born before stars existed. Further observations complicated the story. The companion star was not quite what it seemed. The orbital dynamics were unusual. The black hole may be more like 10 to 20 solar masses, but surrounded by unusual gas structures that made it appear more massive. But the mystery remains. Even a 30 solar mass black hole in the Milky Way is rare and strange. It raises questions about stellar mass loss, metallicity, and the final moments of massive stars. It may suggest new types of supernovae, or direct collapse events where stars implode without a bang. And in the background lurks a deeper idea. What if some black holes aren't stellar at all? What if some are primordial, formed from density fluctuations in the early universe, untouched by nuclear fusion, older than light? LB1 is more than an anomaly. It is a challenge, a cosmic curveball. And like all good black holes, it hides more than it reveals. ChatGPT. At the edge of the visible universe, a quasar roars, not with light alone, but with jets so massive they launch material beyond the bounds of the galaxy itself, forming what astronomers call a galactic fountain. This is HEO 515 to 4414, a hyperluminous quasar more than 10 billion light-years away, powered by a supermassive black hole devouring matter at a staggering rate. As the matter spirals inward, friction and magnetic fields create intense energy, enough to launch jets thousands of light-years long at near light speed. But what makes this quasar unique isn't its brightness. It's what it does to its host galaxy. Using the Hubble Space Telescope and ALMA, scientists discovered that HEO 515 to 4414 doesn't just spew gas into intergalactic space. It cycles it. The gas gets ejected, travels far beyond the galactic halo, cools over eons, and eventually falls back in, seeding new stars, regulating galaxy growth, and reshaping the interstellar medium like a cosmic breath. It's not just a destructive force. It's a circulatory system on a galactic scale. This discovery reshapes how we understand galaxy evolution. Instead of one-way outflows, some galaxies may function like living systems, maintaining balance through these ejection-return cycles. The quasar acts like both furnace and fountain, boiling the center and spraying creation outward. Such fountains may explain how galaxies avoid growing too fast, how they maintain metallicity over billions of years, and why some galaxies remain stable while others collapse. HEO 515 to 4414 is a reminder that even the most violent objects in the universe can participate in creation, not as isolated tyrants, but as part of the larger machinery of cosmic order. The next time you imagine a black hole, don't think only of darkness. Think of the arc of gas glowing in ultraviolet light, curling like ribbons through intergalactic space, and falling, slowly, lovingly, back into a galaxy reborn. In the constellation Aquarius, a red giant star known as V1309 Scorpii performed a vanishing act. Once visible in infrared surveys, it was catalogued as an ordinary, aging star in the final phase of its life. And then, in 2008, it flared violently, increasing in brightness by a factor of 10,000, and then disappeared from visible light altogether. Astronomers were baffled. Had it exploded in a supernova? Had it collapsed into a black hole? Neither. As data poured in, scientists realized what had happened was stranger than either: a stellar merger. V1309 Scorpii was not a single star, but a contact binary, two stars orbiting so close they shared a common envelope. Over time, their orbits decayed, their cores spiraled inward, and eventually, they merged in a flash of heat, light, and shockwaves. But here's the twist: after the outburst, disappear entirely. It reappeared in the infrared, as a swollen, hot, bloated remnant surrounded by dust. We witnessed the birth of a new kind of star, not a main sequence sibling, not a white dwarf, but something transitional, shrouded and embryonic. A kind of stellar rebirth. This event gave astronomers unprecedented insights into how some stars form, and perhaps how red novae and other luminous transients might work. It also hinted at a more universal truth. Many stars we see today may be the product of mergers, and such events might be far more common than we thought, especially in dense clusters or binary systems. The drama of V1309 Scorpii played out over mere months but took millions of years to set up. And now, what remains is a mystery, a ghost of two lives merged into one, glowing dimly in the cold. In the depths of space, far from the warmth of any star, drifts a planet unlike any other, PSO J318.5-22. It's a rogue planet, unattached to any stellar system, floating freely through the galaxy. But it's not cold. In fact, it glows, with internal heat left over from its formation. Discovered in 2013, PSO J318.5-22 is about 80 light-years away and roughly 6.5 times the mass of Jupiter. It's part of a young star group, just 12 million years old, which makes it cosmically young and hot. With no star to reflect or orbit, it emits its own infrared light, a planetary ember in the void. What makes it especially strange is its luminosity and color. It has thick clouds of silicate and iron droplets, producing a reddish glow in the infrared. It's one of the faintest objects ever directly imaged, and yet it shines like a failed star. Its presence raises fundamental questions. How did it form? Was it born in a system and then ejected by gravitational chaos? Or did it form alone, like a star, but simply lack the mass to ignite fusion? Either answer is shocking. If it was ejected, then planetary systems are far more violent than we imagine, and rogue worlds may outnumber stars in the galaxy. If it formed in isolation, then the line between planet and brown dwarf is blurry and broken. PSO J318.5-22 may be one of many. Surveys now suggest the Milky Way may contain billions of rogue planets, silent wanderers, some larger than Jupiter, others the size of Earth, drifting in utter cold. And some may not be lifeless. If such a planet retained enough internal heat, or had radioactive decay, or even a subsurface ocean beneath an insulating crust, life could survive, cut off from starlight, but not from energy. There would be planets of permanent night. No seasons. No sunrises. Only darkness and the faint warmth of memory. PSO J318.5-22 is a glowing ember, an orphan of creation, and a quiet reminder that not all planets need stars to shine. In 2019, a fuzzy dot appeared in the sky, moving faster than any comet previously seen. It wasn't bound by the sun. It wasn't from our solar system. It was from elsewhere. Its name, 2I/Borisov. This was the second known interstellar object, after Oumuamua, and the first confirmed interstellar comet. But unlike the enigmatic, asteroid-like Oumuamua, Borisov behaved much like a normal comet, with a tail of dust and gas flaring behind it. That, in itself, was astonishing. It told us that planetary systems and other stars produce icy bodies like ours. That water, carbon compounds, and perhaps even complex organics aren't unique to Earth's neighborhood. Borisov's composition, rich in cyanide and carbon monoxide, mirrored comets from our own solar system, yet with some surprising differences, such as an unusually high carbon-to-water ratio. It came from the direction of Cassiopeia, hurtling through the galaxy for perhaps millions or billions of years, before intersecting Earth's orbit. It was captured for just a few months before vanishing into the black again, forever outbound. Some researchers speculate it may have originated from a young planetary system still shedding debris, a cosmic nursery flinging ice and rock into the void. Others ask deeper questions. How many such objects pass through undetected? What if one carries prebiotic compounds? Comets be messengers of panspermia, spreading life's ingredients across the galaxy? Borisov was proof that our solar system isn't isolated. Space is not empty. It is a traffic zone of drifting visitors, each one a shard of alien history. And Borisov, in its icy silence, whispered that the chemistry of life might be common, strewn between stars like pollen in the wind. Imagine standing on a planet where the skies glow blue and the winds rage at 5,400 miles per hour. The heat melts metal. But the real horror begins when clouds form, and the rain begins. But it's not water. It's molten rock. Welcome to Koros 7b. This exoplanet, located about 490 light-years away, orbits so close to its star that a year lasts only 20 hours. Its day side is a blazing 4,700 degrees Fahrenheit, 2,600 degrees Celsius, enough to vaporize stone. The night side, however, is drastically cooler, likely hundreds of degrees below zero. This extreme temperature difference creates a stone cycle, like Earth's water cycle, but with lava instead of liquid. On the day side, rocks evaporate, forming silicate vapor clouds. These winds sweep molten minerals to the night side, where they cool, condense, and fall as pebbles or shards of rock. It literally rains stones. The planet may even have lava oceans, constantly churning under a vaporous sky. It's a world where the concept of weather becomes apocalyptic. Yet Koros 7b is only the first of many such lava worlds discovered. Planets like K2-141b and Kepler-10b may share similar traits: scorched faces turned to their stars, boiling rock, and violent atmospheric cycles. They stretch our ideas of habitability and remind us that the universe is full of extreme possibilities. These planets weren't even theorized until recently. Now, we realize rock vapor atmospheres are not only real, but common among ultra-close exoplanets. Koros 7b may be a preview of Earth's distant future, should the Sun ever expand into a red giant. It's a reminder of planetary mortality, and a vision of nature's wild extremes, sculpting planets in fire and returning them to stone. In 2020, a mysterious signal baffled astronomers. It was a fast radio burst, or FRB, a brief, intense flash of radio energy, lasting only milliseconds, yet releasing as much power as the sun in days. Most FRBs are one-time events, But this one, named FRB 180916.J0158 plus 65, repeated. Every 16.35 days, like clockwork, a burst would arrive. It became the first FRB with a periodic cycle, sending the astronomy world into a frenzy. Where was it coming from? Why was it so regular? The source is a dwarf galaxy 500 million light-years away. Theories range from neutron stars in binary orbits, to precessing magnetars, to even speculative ideas involving alien megastructures. What made this signal stranger was its behavior. During a 4-day window, the burst came regularly, then stopped for 12 days, only to start again. That rhythm was unlike anything seen in astrophysics. Some models suggest a neutron star is orbiting a massive companion, and that its radio emissions are only visible during part of the orbit. Others propose the object is wobbling, like a spinning top, with its emissions sweeping across Earth every few weeks. The repetition gives hope. Most FRBs are random, making them hard to trace. But a repeating, scheduled FRB can be studied, targeted, and probed with multiple telescopes. It may help us decode the nature of these strange cosmic flashes. And if some FRBs are artificial, then a repeating signal becomes the most exciting possibility of all. A pattern, a beacon, a pulse in the cosmic dark. FRB 180916 is a cosmic metronome, its rhythm steady, its cause unknown. And somewhere, across 500 million years of space, a mechanism ticks. Orbiting the gas giant Kepler 1625b, 8,000 light-years from Earth, is an object that challenges our very understanding of moons. It's called Kepler 1625bi, and it's possibly the first exomoon ever discovered, and a gigantic one. Roughly the size of Neptune, this moon is unlike anything in our solar system. If confirmed, it would be as large as a planet, yet orbiting another planet. Are staggering. In our own system, moons form through co-accretion, alongside their planet, capture, or collisions. But none of these mechanisms can explain a gas giant-sized moon orbiting a gas giant. It's like finding a tennis ball orbiting another tennis ball, both the size of cities. Some scientists speculate this object is not a moon at all, but rather a captured binary partner, a cosmic dance frozen in orbit. Others wonder if this system is a scaled-down version of a star-planet pair, blurring the lines between moons, planets, and even brown dwarfs. The detection, made using the Hubble Space Telescope, was indirect, through transit timing variations and subtle dimming in light curves. Critics say the data is thin. Supporters argue it's the first whisper of a new class of celestial bodies, exomoons larger than anything we've imagined. If these supermoons are real, they could be common, even habitable. A Neptune-sized moon around a Jupiter-sized planet, in the habitable zone, could have complex climates, magnetic shielding, and even liquid water. And from its surface, the planet would loom in the sky, a permanent, massive crescent filling the heavens. Kepler 1625bi could be a missing link, a glimpse at how planetary systems evolve beyond our narrow solar template. Or it could be something stranger, an object that defies categories, born from processes we have yet to imagine. Tatooine, the desert world from Star Wars, had 2 suns. Reality, as it turns out, goes further. Meet GW Orionis, a star system about 1,300 light-years away in the Orion constellation, containing 3 stars and a massive, misshapen circumtriple disk of dust and gas. What astronomers found in 2020 was that this disk, unlike others, was torn and tilted, forming a warped ring. And embedded within that ring could be one of the first planets ever found in a stable orbit around 3 stars. This is not just poetic. It's gravitationally bizarre. Triple star systems are notoriously unstable. Their gravity pulls and stretches any planet's orbit, often making it impossible for planets to form or survive. But simulations show that the disk around GW Orionis could be massive enough and coherent enough to birth planets within its warped folds. If confirmed, a planet here would experience triple sunrises, braided light, and seasons beyond anything on Earth. The planet would orbit all three stars, bound not to one but to the entire system. Its sky would be a theater of synchronized motion, a ballet of glowing orbs crossing and receding. It challenges our models of planet formation. Most planetary theories assume a single, stable star. But GW Orionis shows that chaos can still give rise to order, and that planetary birth may be far more resilient than we knew. Planets around multiple stars might be common. And if they are, so too may be alien life under braided sunlight, evolving beneath three shadows. In 2019, researchers studying a meteorite that fell in Australia made a shocking discovery: stardust older than the Sun. Microscopic grains, trapped in the Murchison meteorite, were dated to 7 billion years old, more than 2 billion years older than the solar system itself. These grains are called presolar grains, and they formed in the dying atmospheres of ancient stars, long before our Sun was born. They are cosmic refugees. When a star like our Sun nears death, it swells into a red giant and sheds its outer layers. In this vast wind, silicon carbide crystals can form. These grains are then ejected into space, where they drift for billions of years before becoming part of new star systems. In this case, they found their way into a meteorite, a remnant of the early solar system, and eventually to Earth. The grains carry chemical fingerprints of their origin, isotopic ratios that match stars of specific types and ages. They are time capsules from other stars, older than anything on Earth. Studying them gives us insight into the life cycle of stars, the formation of the galaxy, and the cosmic mixing bowl that birthed us. They are also humbling. In your hand, you can hold something older than the Earth, forged in the death throes of a star that vanished before our solar system began. It is a reminder that we are not only stardust, we are old stardust. That long before there was an Earth to fall upon, the dust had already begun its journey. ChatGPT in the large-scale structure of the universe, galaxies are not scattered randomly. They form a vast, sponge-like web, clusters and filaments surrounding enormous empty regions called cosmic voids. But one of these voids, the Bode's void, is so massive and so empty that its very existence defies explanation. Discovered in 1981, the Bode's void spans over 330 million light-years in diameter. It's not just large, it's staggeringly vacant. Within this space, there are thousands of times fewer galaxies than expected. It contains only about 60 galaxies, when it should host thousands. It's sometimes called the Great Nothing. How did such a vast region form, seemingly untouched by the same gravitational dance that shaped the rest of the cosmos? Theories include a colliding supervoid, multiple voids merging into one mega-emptiness, a rare primordial fluctuation in the early universe's density map. Even speculative ideas, like interaction with exotic matter or the effect of hidden dimensions shaping cosmic flows. Some models suggest that galaxies once existed there, and were somehow pulled away, creating an unnatural cavity. But others propose it was always this way, a bubble in the foam of existence. A region where matter never condensed, never clustered, never lit up. From Earth, it appears as a faint region in the Bode's constellation, dark, underwhelming, yet impossibly vast. What's more, light traveling across the Bode's void experiences less gravitational lensing, fewer interactions, and a slightly different cosmic microwave background imprint, making it a useful laboratory for studying the early universe. It is not merely emptiness. It is an anomaly of absence, one that stretches our models and hints that the universe might be more uneven, more chaotic, and more peculiar than we dared imagine. ChatGPT. In the farthest observable reaches of the cosmos, astronomers have discovered something strange: massive, silent galaxies that should not exist. These are galaxies that formed more than 12 billion years ago, just a few 100 million years after the Big Bang, and yet by the time we observe them, they're already dead. Their star formation has stopped. Their gas is gone. They are enormous, full of red, aging stars, and entirely quiescent. One such example is ZFOURGE-1, discovered in deep field surveys using the Hubble and Spitzer space telescopes. It's a massive galaxy that, by redshift, existed when the universe was less than 1.5 billion years old, yet it was already mature and quiet. How could galaxies so big form so fast? And why did they shut down so early? Theories abound. Some suggest a burst of star formation, a cosmic flameout that used up all available gas in a short frenzy of birth. Others propose that black holes at their centers heated or expelled the remaining gas, halting further growth. These galaxies defy the standard timeline of galaxy evolution. In the early universe, galaxies were supposed to be small, clumpy, and vigorous. And yet here we find giants, silent, smooth, and ancient, as if they aged at 10 times the normal rate. These findings shake our models. It may mean that the universe built structure faster than we expected, and that the earliest galaxies were more efficient, more aggressive, and more complex than anything in our simulations. The silent giants tell us that the past was not quiet. It was a place of roaring births, swift deaths, and cosmic overachievement. And they still float there, invisible to the naked eye, whispering of a time when the universe did not yet know how to grow slowly. Deep within the constellation of Dorado, roughly 160,000 light-years away, lies a star that is spinning so fast, it's reshaping itself, literally. Its name is VFTS 102, and it rotates at more than 2 million kilometers per hour at its equator, so fast, it's nearing the breakup speed. Any faster, it would begin to tear itself apart. This rapid rotation flattens the star into an oblate spheroid, its equator bulging out, its poles compressed. It's not round. It's a stellar pancake, distorted by sheer velocity. Such rapid spin is rare. Most stars rotate, but nothing like this. And this speed has profound effects. The star's surface temperature is uneven, hotter at the poles and cooler at the equator, due to a phenomenon called gravity darkening. It flings stellar wind from its equator, shedding mass in a disk-like halo. It distorts its internal structure, mixing its core and extending its life, even as it races toward collapse. How does a star get this fast? One theory is that VFTS 102 was once part of a binary system. When its companion went supernova, it may have transferred mass and angular momentum, spinning VFTS 102 into a blur and slingshotting it out into space. Now it drifts alone, a cosmic gyroscope, its past companion long gone, perhaps collapsed into a neutron star or black hole. Eventually, VFTS 102 may explode in a gamma-ray burst, a violent end driven by its rotation. Such bursts are among the brightest events in the universe, capable of sterilizing entire regions of space. But until then, it spins, silently, relentlessly. A reminder that stars are not serene spheres, but dynamic, unstable machines, and sometimes they dance too fast for comfort. Space is cold. Deep space is colder. But there's one place that is, strangely, colder than the background temperature of the universe itself. It's called the Boomerang Nebula. Located 5,000 light-years away in the constellation Centaurus, this nebula has an internal temperature of just 1 Kelvin, that's -272.15 degrees Celsius. colder than the 2.7 Kelvin temperature of the cosmic microwave background radiation. It is, by all known measures, the coldest natural place in the universe. How is this possible? The Boomerang Nebula is a preplanetary nebula, the early stage of a dying star shedding its outer layers. In this case, the gas is being expelled so rapidly and efficiently it cools dramatically through adiabatic expansion, the same principle behind how your refrigerator works, but on an interstellar scale. As the gas races outward at over 160,000 kilometers per hour, it loses energy and cools. The speed of this expansion causes temperatures to plummet, below the background radiation itself. In visible light, the nebula appears ghostly and faint, but in radio and submillimeter wavelengths, it becomes a frozen hourglass, leaking gas into space at bone-chilling speeds. This cold environment is not just a curiosity. It preserves complex molecules, allows for ice formation, and might offer a rare glimpse at the chemistry of dying stars before they explode or fade. One day, the central star will heat again, lighting up the gas in a dramatic transformation into a planetary nebula. But for now, it's a cold whisper in the cosmic dark, a place colder than the light that fills the universe. A cosmic contradiction. ChatGPT. In 1967, a strange, regular radio signal was detected from space. It pulsed like a heartbeat, so precise, so unwavering, that the scientists who found it briefly considered the possibility of aliens. They even labeled it LGM1, Little Green Men. What they had discovered was the first known pulsar, a spinning neutron star, the collapsed core of a massive star that has gone supernova, now rotating rapidly and emitting beams of radiation from its magnetic poles. But one pulsar, in particular, defies even these strange expectations. Meet PSRB 1931+24, a pulsar that behaves like a cosmic switch, turning its signal on and off every few weeks. When active, it pulses at a precise 0.81 seconds per beat. But after a week or so, it goes completely silent for about 25 days. Then it switches back on, like clockwork. This on-off behavior is unlike anything else in the pulsar catalog. Even more bizarre, when the pulsar is off, its spin rate slows down less rapidly. When it's on, it spins down faster, as if the act of emitting radiation is actively braking the star. It's the only known pulsar with such behavior. One theory is that the pulsar is periodically choking on its own plasma, unable to maintain the complex magnetic interactions that create its beam. Another theory involves magnetospheric switching. The entire magnetic field structure of the pulsar may be flipping between two modes, like a cosmic heartbeat with a missing beat. This is not just a curiosity. It may hint at a hidden class of neutron stars, ones that pulse in irregular, selective patterns. It suggests that we may have missed many pulsars simply because they weren't on when we looked. Some may blink once in a year, others once in a century. The sky may be filled with ticking clocks we've never heard, silent now, but waiting to turn back on. Some planets are strange because of how they form. Others are strange because they survive against all odds. WD 1856b is a Jupiter-sized planet orbiting a white dwarf star, the remnant core of a dead sun-like star. This in itself is shocking. White dwarfs are created when a star like our Sun exhausts its fuel and swells into a red giant, consuming and incinerating everything within several AU. In that final act, it engulfs and destroys its interplanetary system. And yet here is WD 1856b, intact, orbiting just 2 cents from its white dwarf, completing a full orbit every 34 hours. How is it still there? It likely wasn't. The planet must have started out farther away, only to later migrate inward, a feat that would require precise gravitational interactions, possibly with other planets or a third star. This implies that planetary systems can reconfigure even after their parent star dies, like reshuffling the deck after the game is over. It also hints that other white dwarfs may harbor hidden planets, tucked into close, tight orbits we've yet to detect. Even more astonishing, white dwarfs are cool, stable, and long-lived. If a planet can survive the chaos and settle into a tight orbit, it may bask in gentle, infrared heat for billions of years. Which means, the graveyard of a star may become habitable again. And we may be underestimating how many worlds are born again from cosmic death. ChatGPT. When we think of planets, we imagine spheres, solid, stable, orbiting quietly around their stars. But one exoplanet, known as GJ436b, defies this image entirely. It has a tail. A vast, comet-like plume of gas and particles that trails behind it for millions of kilometers. This planet, a warm Neptune, orbiting a red dwarf star just 33 light-years from Earth, is literally being boiled away by its star's radiation. GJ436b orbits extremely close to its star, completing one full trip in just 2.6 Earth days. This proximity exposes it to a bath of extreme ultraviolet radiation, which heats its atmosphere until it begins to escape into space. The result is a hydrogen cloud so vast it eclipses the star. The planet is only 4 times the radius of Earth, yet its tail stretches 15 times longer than the Sun's diameter. This process is called atmospheric escape, and it's not uncommon for close-orbiting planets. But the sheer scale of GJ436b's outflow was unexpected. It loses about 1,000 tons of material per second. Strangely, the star itself is not particularly active. It doesn't emit strong flares or have high X-ray output, which means something else may be helping to drive this escape. Some scientists propose the planet's gravity and magnetic field are shaping the flow, funneling gas into this strange, extended tail. Others suggest interactions with stellar wind create a comet effect, sculpting the cloud into its peculiar form. This discovery is more than visual spectacle. It's a window into planetary evolution. GJ436b may once have been a gas giant, now being stripped down to a rocky core. In time, it could become something completely different, a new type of world, forged by radiation and loss. In space, even planets have life cycles, and sometimes they leave a trail of their transformation across the stars. Black holes are the ultimate destroyers, swallowing stars, erasing light, compressing space and time into a single, silent point. But in the heart of galaxy IRAS F11119+3257, hole that is doing the opposite. It's creating stars. Here's how. This galaxy hosts an active galactic nucleus, AGN, a supermassive black hole feeding on nearby matter, surrounded by a spinning accretion disk and blasting powerful outflows of energy into space. In most cases, this outflow suppresses star formation, heating and expelling gas. But in IRAS F11119+3257, the outflow seems to be compressing nearby clouds of gas, squeezing them into dense knots where new stars can form. This is known as positive feedback, a process where a black hole doesn't just regulate star formation, but catalyzes it. It's like a forest fire that accidentally triggers new growth. Using data from telescopes like ALMA and NuSTAR, astronomers detected molecular outflows moving at over 1,000 kilometers per second, shaping the environment like a sculptor with breath. The winds don't simply blow things away, they sculpt and ignite. This rewrites a long-held belief that black holes only quench galaxy growth. Instead, they might be essential to galactic renewal. In the paradox of cosmic mechanics, destruction fuels creation. And within the blast radius of a black hole, in the heart of chaos, stars are born. ChatGPT. Deep in the constellation Centaurus, about 50 light-years from Earth, lies BPM 37093, a white dwarf with a secret buried in its heart. This is no ordinary star remnant. It has crystallized. Nicknamed the Diamond Star, BPM 37093 is the carbon-oxygen core of a dead sun-like star that has cooled and condensed over billions of years. As white dwarfs age, their interiors undergo a phase transition. Carbon atoms begin to lock into place, forming a rigid, crystalline lattice. Essentially, it has turned into a giant cosmic diamond, about 10 billion trillion carats in size. The idea sounds fanciful, but it's rooted in real physics. Stars like our Sun end their lives shedding their outer layers, leaving behind a dense, Earth-sized core. This white dwarf retains about 60% of the Sun's original mass, squeezed into a volume the size of Earth. Its gravity is so immense that a teaspoon of its material weighs several tons. In 2004, astronomers used pulsation measurements, stellar seismology, to probe BPM 37093's interior. They found evidence that a large portion of the star had indeed solidified into a crystalline form. It glitters in silence, its diamond core invisible to telescopes, but predicted by theory and confirmed by vibration. In the far future, all white dwarfs will eventually crystallize as they cool. This includes our own Sun, which will collapse into a similar form, and over trillions of years, become a faint, glowing jewel in the night. A diamond buried in the void. Not as metaphor, but as matter. Ever since the Big Bang, the universe has carried with it a relic, the cosmic microwave background radiation, CMB, a faint glow permeating all of space, the afterglow of creation itself. It's the most ancient light we can see, and one of the most precisely measured datasets in science. But hidden within this glow is a subtle pattern, a curious alignment of temperature fluctuations that seems far too orderly to be random. Scientists call it the axis of evil. When the CMB was mapped by WMAP and later by Planck, researchers noticed that the largest scale fluctuations in the sky, the quadrupole and octupole moments, were aligned in a single direction. This alignment wasn't expected. According to the cosmological principle, the universe should be isotropic, roughly the same in all directions. Yet here was a preferred direction in the ancient light. What caused it? Some say it's a statistical fluke. Others suggest residual contamination from our galaxy. But more exotic explanations abound, that the early universe was shaped by cosmic topology, curled space, twisted dimensions, or remnants of cosmic strings. That the inflationary field responsible for the Big Bang had a built-in asymmetry. Even whispers of the multiverse, that our universe was bumped or influenced by others in the earliest moments of time. Whatever the cause, the axis of evil remains. It stretches across the entire sky. Scar in the most ancient light. It's not a signal in the usual sense, not a transmission, not a message. But it is structured, and structure is meaning. And sometimes, meaning is more terrifying than a message, because it implies intent, or at least order. And in the cosmic background noise of all things, that is perhaps the most unsettling thing of all. We began with Oumuamua, the strange visitor that tumbled through our solar system, not with answers, but with questions. From there, we crossed the haunted edges of black holes, skimmed the surface of shattered planets, listened to ancient pulses, and glimpsed the shimmer of diamond stars suspended in darkness. But now, as we close our eyes, it's not the noise of the cosmos that lingers, it's the silence. The silence between pulses. The hush after a flare. The pause between theories. The quiet between the stars. There's a peculiar kind of wonder in the things we almost understand. In the evidence that nearly fits. in the glow that fades just before we can grasp it. The universe is not indifferent, it is eloquent in riddles. It speaks not in certainties, but in tantalizing maybes. In facts so shocking they feel like fiction, and truths too strange to fit neatly in textbooks. We once believed the stars were eternal. Then we learned they die. We thought black holes devoured everything. Now we find they might seed galaxies. We thought life must look like us. But the more we search, the more we suspect we are the anomaly. The cosmos is not a theater built for human observation. It is a slow-burning, unending canvas, soaked in silence, riddled with shadows, pierced by light, folded in dimensions we do not yet have the language to describe. And yet here we are, listening, wondering, drifting. Every comet, every pulse, every cooling core is a story. Some are loud. Others, like the cold whisper of the Bodhi's void, or the dim flicker of a dying red dwarf, speak in lullabies. We don't need to invent myths. The truth is already too fantastic. Tonight, let these truths carry you. Let them lull your thoughts into orbit. Let the strangeness of it all be a blanket. Let your dreams drift through pulsar winds and gravitational waves. Let sleep arrive like a planetary eclipse, gentle, slow, and complete. And when you wake, the stars will still be there. So will the questions. And the wonder. Always the wonder.